Hey everyone, well, welcome back. So in this video, what we're going to do is we're going to spend a little bit of time talking about different properties of waves, how they behave maybe on their own, or how they would behave in the presence of another wave on the same medium, things like that. Now, I just want to preface this by saying, I'm just here in my office by myself. I don't have the equipment that I would need to demonstrate some of these things in this particular video. But what I'm going to do is in the show notes, the episode notes, I'll post links to other YouTube videos that demonstrate these particular phenomena. Okay, so with that said, let's begin. All right, so the first property we're going to talk about is something called the phase of a wave. Okay, now what is the phase of a wave? Well, basically it represents points on a wave. Okay, different points are at a different phase. Now, you can be either in phase with a certain point, or you can be out of phase with a certain point. When you're in phase, you're at the same point on that wave. Okay, to be a little bit more physicsy with it, you're in phase if you're integer multiple wavelengths apart. So, for example, all crests are in phase, all troughs are in phase with each other, right? So, I'm going to draw some pictures on it to kind of represent that a little bit more, but that's a general kind of definition with it. And when you're out of phase, you're at different points on a wave. So, a crest and a trough are out of phase because they're not the same kind of point. So let's draw that picture and let's see how that works. Now what I'm going to do is on this whiteboard I'm going to draw a transverse wave. All the things we're going to be talking about still would work for a longitudinal wave, but just again, it's easier to draw a transverse wave than it is a longitudinal wave in a way that's clear and concise and easy to label. Okay, so let's draw this. Okay, so here we go. We have our nice transverse wave. Okay, here's our equilibrium line. Here's two full wavelengths of this transverse wave, right? So it starts here, goes up, that's one wavelength, there's another wavelength. All right, now I'm going to label different points on this wave. We're going to kind of go through which ones are in phase, which ones are out of phase. Okay, so right there, A, B, C, D, E, F, G, H, I, J, K, L, and M. Excellent. Okay, so let's take point A here, for example. Okay, we're on the equilibrium line. Which point or points will be in phase with point A? Well, remember, you have to be an integer wavelength apart and at the same spot. So if I take point A, okay, well, none of these points are on the equilibrium line, so we know they're not in phase with there. We have D, D's an option. Okay, E and F, not so much, again, because they're not on the equilibrium line. G is an option. H, I, J, not on the line. K is an option, not L, M. So right now we have A, D, G, K, and M as options to all be in phase with A. But remember that other part of the definition. To be in phase, you have to be at that same spot, just being a full wavelength apart. A and D are only half a wavelength apart. If you were to trace this, you'd start by going up at point A, but then down at point B. They're not the same kind of point. So let's follow through knowing that new bit of the definition, right? They have to be doing the same thing while also being at the same spot, right? So we say A is up, okay, D is down, out of phase, go through, G is up, hey, look at that, A and G are in phase, they're on the equilibrium line, and they're both doing the same thing, follow through, not K, but M is, okay, so A, G, and M are in phase, okay, B and I are in phase with each other, right? They're both at crests. F and L are in phase. They're both at troughs. Okay? B and F are not in phase, even though they're at peaks. But since B is at a crest and F is at a trough, they're not in phase. Okay? Now, let's take a look at C. Well, we want to make sure it's at the same kind of spot, but also doing the same thing. Okay? So not down there. No. Oh, H is at the same spot, but if we kind of trace our line here, C is going down, H is going up, not the same. Come back around, oh look, J. J and C are in phase because they're doing the same thing and are at the same kind of level on the wave. Okay? So that's just a basic picture of what it means to be in phase or out of phase. All right, so that's phase. The next one we're going to talk about is something called resonance. So let me quickly write down the definition of resonance. Resonance. Okay, it's adding little bits of force to create larger motion. Okay, so this is one of those ones where I don't have the equipment here to really demonstrate resonance, but what I'll do again is I'll post a link to a demonstration for this. Okay, now, where might you see something related to resonance? Well, I'm sure you've heard about opera singers and the way they sing can break glass. Okay, well, that can happen. It's very difficult, but it can happen. The only way it can happen is if that opera singer is singing at a frequency that the glass can vibrate at. Okay, so it's got to be high enough to get that glass to vibrate, and as you're increasing that vibration, eventually the glass breaks. Okay, another example of resonance would be the radio in your car. Let's think about this for a second, right? Pick a radio station that you like to listen to. K104, WRRV, whatever it happens to be. I like 101.5, so I'm going to stick with that one. Okay. FM radio stations resonate at the megahertz kind of range. So that's 1,000,000 hertz. So 101.5 would be 101.5 megahertz. Okay. That means the radio station is emitting these radio waves at that frequency. If I want to listen to that station, I have to tune my radio so that the antenna is able to vibrate at that frequency. So basically what happens is the radio waves hit the antenna, cause the antenna to vibrate at that frequency, and then the signal is then interpreted by the electronics in my car or in my boombox or whatever it is I'm listening to convert into sound waves so I can hear the different songs. That's resonance. Okay? Again, in order to see this in another way, check out the videos that you can find in the links below. Okay? Now, this next one is a little bit of a biggie, so it's going to take a little bit of time to go through completely, but it's still very, very important. Okay? So this one is called superposition. Now, with superposition, that is the addition or subtraction. I wrote a P, not a B. Let's fix that word. Sorry. Subtraction of amplitudes. Okay, so superposition is when you add amplitudes or subtract amplitudes depending on how the waves are. Now, it's important to note that you need 2 or more waves on the same medium in order for superposition to take place. Okay? Now, when it comes to superposition, obviously there are 2 different ways it can happen. You can add the amplitudes or you can subtract the amplitudes. Now, we have names for those things. So, adding the amplitudes is called constructive. Think of construction, you're building something, right? Constructive interference. Okay, this is the addition of wave amplitudes. Okay, comes in 3 phases. So step 1 is when you have the 2 waves just kind of minding their own business, heading towards each other. Okay, so here's the medium. This bump is one wave. This bump is the other wave. Okay. The next phase is, or the next step is when they meet. Okay, they're going to meet, and because they're both on the same side, you know, they're both kind of above, they're both crests, they're going to add up, right? So if this was 1, this was 1, this becomes 2, right? Now if this were 2 and this were 1, this would be 3, right? It's just a straight up addition. Now, what's important is what happens after. what happens after is the waves just pass through each other as if nothing happened. So this wave was this one. It just kind of kept on going. This wave was this wave. It just kept on going. It just happened to be in the middle. They met and they added up real quick. Okay. The next one is called destructive interference. Okay. Now, if you kind of piece things together, knowing that constructive interference is the addition of waves, destructive interference is the subtraction of waves. Okay, so again, three-step process. Step one, have the waves come towards each other on the same medium. Okay, now the key thing here is you have one wave as a crest, one wave as a trough. Okay, then step two, they're going to meet. Now, what happens in step two depends on the amount that their amplitude is. Let's for now say this is 1 and this is also 1. So when they meet, they're going to completely cancel out. And you'll get just a straight line. You know, if this were 2 and this were 1, you'd get a little bump and vice versa, right? It's just a straight up subtraction. And then again, in the third step, it just passes along as if nothing happened, right? So this trough just kept on going. This crest just kept on going, right? It was just in this instant their energies sort of caused a cancellation almost. Okay? So that's constructive and destructive interference and superposition in general. Those concepts can be found in videos, again, linked below. Okay. All right. We've got one or two more. Okay. All right. Yeah, just one more. I'm just checking my notes, make sure I don't miss anything. That last one is going to be standing waves. And the way standing waves work is you have a single wave interfere with itself. So it looks like it's standing still. Okay. So single wave interfering with itself so it looks like it's standing still. Now, I know earlier in the video I happened to say that well, you need two waves on the same medium in order for it to interfere, blah, blah, blah. Well, what happens is, if you have a wave that is on a medium and it is bound on both ends, so think of a guitar string, right? Either end, it's stuck, right? It can't move anywhere, versus, say, a slinky. If you were to hold one end and wiggle the slinky, that other end just kind of flops all around, okay? You're not going to get that effect for something like that. But for like a guitar string, piano string, something like that, the wave will travel down the string, hit the end, and then bounce back. Okay. Now, what does a standing wave look like? Well, let me draw a picture of it. Okay. So here's an example of a standing wave. So the wave started here, traveled this path, hit this boundary, and when it reflected off this boundary, kind of bounced back the other way and interfered with itself via a combination of destructive and constructive interference to create this kind of pattern. Now, if you were to see this in real life, you'd kind of see these bits vibrating up and down, or side to side, depending on what plane you're looking at. A video for this can be found in the links below. Now, what's important about this is where certain parts of this standing wave are, what we call them, and that helps us figure out things like wavelength, frequency, speed, so on and so forth. Now, this point right here, this point right here, this point right here, this point right here, these are called nodes. Nodes are the points on the wave where you have maximum destructive interference, so it looks like there's no movement there. Okay? But then we have points like this here either the crests or the troughs. You can't count both for one, so each chunk is kind of its own bit. Those are called antinodes. Creative, I know. Okay. Now, we use standing waves all the time. The way I'm speaking is by creating a standing wave within my throat, at which point my vocal cords can then vibrate the air, which then is projected out into the overall air, which then is picked up by the microphone, which is then converted into ones and zeros within the electronics of the phone, and so on and so forth. And the opposite kind of thing happens in your videos that you're watching, right? So these are some important ideas, some important properties of waves. We use these things to study sound and light, which is going to be studied in another video. So with that, see you later.